So this becomes 2x squared. Again, the negative is still positive. What about a negative number that's been cubed? Like negative 3 cubed is what? Negative 27. So a negative cubed is indeed negative, right? So what's going to happen here is this. Here, the negative sign is going to remain, but we have a negative negative, which makes this sign positive now. Again, this negative is here. This is indeed negative. So negative negative makes this positive. Over here, negative negative makes this. Come on, people. It's very easy. I'm prompting you. Positive, thank you. And clearly a constant doesn't change. So that's what p of negative x is. So, simply put, what can we do whenever we want to find a function of negative x? Switch the signs of all the terms with
a positive.
Come on. X to the fourth was positive to start, it still is positive. X to the second was positive, it still is positive. X to the third and x happen to be negatives in front, and they became positives. I understand that it looks like to switch negatives to positives, but clearly that's not true because we didn't do that for the last one. So what's the rule?
For every term with a variable is positive.
Close. I can see why you're saying that. I can see why you're saying that.
Every term with the variable and an odd exponent changes sign.
Yeah. Why do we change the sign? Because an odd, a number that's negative to an odd power is still negative. But a number that's negative to an even power is really positive. That's our rules of exponents. So whenever you see an odd exponent, please jot this down with asterisks. When you see an odd exponent, just switch the sign to give you p of negative x. Now, look at the number of sign changes. Go down to the bottom, please, where you see that. Look at the number of sign changes. Are there any sign changes there? How many? Just one. It's right here, on the far right. It's the only sign change. So this function has at most one, what do you think? Negative. Very good. Okay, if the other one's positive, this one's probably negative. Now, what Charles was mentioning a moment ago is what we can touch upon now. What we can have is this. We can have one negative and three positive, easy, because our function was x to the 1 power. Fourth, 1 plus 3 is clearly 4. Are we done already? I want you to look up. I'll give you a minute to write that. I'm going to point to stuff, so I want you to see what I'm looking. So again, we could have one negative, three positive. And that gives me 4 roots. But if for some reason some of these roots are not real, say there's a pair of imaginary roots, right? That takes up 2 of my roots, leaving behind 2 other roots that could be real. Well, only one could be negative, right? So only the other one could be positive. And that's what Charles, you were getting at the fact that they differ by 2, right? When you go down. So if I had, here's my options for this scenario. Let me just write it out to make a little more sense of this. Okay, I'm going to make a little table to show you what I'm talking about. So we could have, here's the possibilities. Let's go with real and imaginary. So case 1. Within the real case, we have negative and positive options. And then we have imaginary. So case 1. We could have 1 negative and 3 positive, totaling 4 roots, which makes sense. We could have, and with 0 imaginary then. We could have 2 imaginary because they come in pairs, but we can only have 1 negative, which was stated earlier, so we can only have then 1 positive.
Doesn't it actually have 3 positive real roots then?
At most, at most.
Oh, okay.
It's not dictating the actual number, okay? So if we get a pair of imaginary roots, it takes away 2 from the positive column. This value has 3 most roots. You can only go down by 2s, is what he was getting at. So if this was a 5 possible positive roots, you could have 5 or 3 or 1. It always goes down in pairs, always in pairs. All right, let's look at an example of this, okay? Let's look at an example of this so we can see what's going on. 1 times -4 is -4 plus 3 is going to give us -1. -1 and 2 is going to give us +1. So that's what happens here. So what's going on with this problem is, yeah, it's possible that there's no rational roots, but there's definitely a root between 1 and 2 because your sign switched here. Okay, we can try the other two, just to make sure. Let's see what the other two look like. So let's try -1. It's going to be -1 and -5 is -6. 6 and 3 is 9. -9 and 2 is -7. So that's a lower bound, right? So there's not going to be another root below this number. So I don't need to try -2. Again, alternating signs tell me this is a lower limit. I'm not going to get a rational root below this number. So it means try a number that's larger than it. But this is the smallest number we have. No number bigger than we haven't tried yet. So that's all we know from this. So yeah, it means it must be irrational. So let's look between 1 and 2 on our graph. Go ahead and graph this in your calculator. So right next to 1, it looks like there's a root. Look to the right of 1. If you need to zoom in, make your window settings. Go on the x-axis from like -4 to 5, and on the y-axis -2 to 2. For your x min, x max, y min, y max.
-4 to like 5.
Okay? Yeah, so this is my window. I don't have my computer with me. I went from -4 to 5 on the x-axis. So it zooms in a little bit on the graph and looks a little bit nicer. Okay? So I can see all 3 roots here. It's clearly not on 1. And it's not on, looks like 4. It looks like these are all irrational roots in this case. Let's try and figure out what the first root is. Second calc. So the first root we get is this. Well, let me just write it as a coordinate. That's the root on the negative side of the axis that you're looking at. Kelly, focus on math. The second root I'm getting is 1.227. And it looks like there's no repeating patterns in the first at least 8 digits of these. So we're looking at here irrational values. I wonder why we're getting 3 irrational roots. So they should be coming in pairs. Let's see if we get the third root. .164. Interesting. This is what the 3 roots you got in any of these?
So, no, irrational roots usually come in pairs.
I'm saying, I wonder why we're getting 3 irrational roots. I'm thinking off the top of my head that And one of these sets is a pair. I'm trying to think of which would be equidistant on either side. 8164, 227. I don't know. I gotta think about this. Let me think. I don't know. It's an interesting fact. Why would we get 3 rational roots there? Let's see. Let's try one. Try one that will work for sure. So, who was I showing this the other day? Wolfram Alpha. Who did I show it to? I was working with somebody, Mike. So, 2x to the 4th minus x cubed minus 11x squared minus 8x minus 12. So, let's go through the process again. How many sign changes do you see in the original function right here? How many sign changes? 1. So there's, at most, 1 positive real root. Now remember, if I want to know and look at f of negative x, or if I want to look at the odd function, if you will, what do I have to change? What was the rule that I told you guys? We went over this together, we did it, and then we kind of like came to a conclusion.
Take f of x, f of negative x.
Good, and what does that do to the whole function in turn?
Like change those signs around.
Of which ones?
Of the ones with x going instead of
That are?
odd.
Odd, very good. Remember, when you square an even that's negative, it's still positive. So even if I negate all these, if I make this negative x squared here, or x to the 4th, it becomes positive. But if I make this a negative here, it becomes negative x cubed times another negative here, making that a positive. So switch all of your odd exponents, remember. So switch these two right here. Leave all the even exponent ones the way they are. If that's not clear to you, please come see me. Come ask me and I'll go over it. I'll do an example with you with numbers. We'll plug in numbers and I'll show you that's true. So how many sign changes do you see now? How many? 1, 2, 3. Oh, sorry, the first one's not right. I apologize. And the third over here. So at most 3 negative real roots. All right, so how do we do this? We look at our P's and Q's. The values of P, we have 1, 2, 3, 4, 6, 12. Q is simply 1 and 2. Unfortunately, we have a possibility of positive and negative roots based on our Descartes rule of signs at the beginning. So we can't rule out the negative roots, so we're going to put plus or minus here for P's and Q's. Let's look at all of our ratios real quick. It's pretty easy to look at these ratios though, right? Why is it pretty easy for these? A lot of them are what? A lot of them are over 1, and then the other ones, a lot of them are multiples of 2. So it makes reducing by 2 very simple, and a lot of our roots cancel. So start with let's start with the smallest number for this case. We've got 1 over 1, 1 over 2. 2 over 1, and then I would write 2 over 2, but I've already got 1 over 1, so I'm not going to write 2 over 2. Or I could write it and then do this, if it helps. 3 over 1, 3 over 2, 4 over 1, 4 over 2, which doesn't matter, because we have 2 over 1, 6 over 1, 6 over 2, which also doesn't matter, and then finally 12 over 1 and 12 over 2, but 12 over 2 doesn't matter. So I cross it out. So it looks like I've got the following values as possibilities. Simplifying, we've got 1, 1/2, 2, 3, 1.5, 4, 6, and 12. So what might you do? These are plus or minus all these. What might you do in a situation like this? Honestly, imagine you didn't know the roots. How would you approach the next step? Without calculating now, because we're doing this with Descartes rule of signs. How would you approach the next step? What would be a good step? Because you could take several options here. Why would you make the next step that you're going to make? Why?
To see if you can find your lower bound and your upper bound.
Okay, to see if one of them is at least the lower and upper bound. Good. That's one way to start. What else could you do? There's another way to approach it, actually. What's the opposite of starting at the ends?
Starting in the middle.
It might be useful to start in the middle once or twice. I'm thinking about this now because if one of those is an upper or lower bound, you know search all above or all below. So you just cut your data in half. Follow what I'm saying? So let's start with the middle one first. Let's try this technique. And I was thinking about this last night. The idea of this is like a search domain theory. You pick something in the middle, which tells you if one of those is an upper or lower, that you can either look above or below. If it's not, it doesn't work, right? So that's unfortunate. So we might not get any data. But we can try it once with these. So let's try it. So what's the number that's in the middle of these? 3. Now remember, these are all positives and negatives. So you're really going from 12 to negative 12. So what's in the middle there? 1 or negative 1 will probably be the easiest, right? 1/2 is obviously closer to 0 really, but 1 or negative 1 would be easy to try. So let's try 1 or negative 1 first. Our numbers across the top of our synthetic table are going to be 2, negative 1, negative 11, negative 8, and negative 12. And let's try 1. Bring down the 2. 1 times 2 is 2. 2 minus 1 is 1. 1 times 1 is 1. 1 minus 11, negative 10. Negative 10 and negative 8 is negative 18. Negative 18 and negative 12 is negative 30. So does this give us any information about this? It doesn't give us anything except for this one fact. When you plug in a 1, you get negative 30. That's your y coordinate. That's all it gives you. It's an x and y. So now at this point, let's try another value that's maybe a little bit bigger, a little bit smaller. If we get a positive remainder, what does that tell us though? Somewhere in between. So if we can find another one that gives us a positive remainder, at least we know it's in between them. So pick something nearby that has other possible rational roots between it. So look at the list. If I choose something like 4, and I get a positive, at least I know that either 3 or 2 will work, or maybe 1.5 will work. Maybe I'll choose 3, so my search domain is a little smaller if it's correct. You see the method in which I'm choosing here? That's really all you can do with this. Okay, until you get some sort of a pattern that gives you some evidence. Yeah.
Try 3.
Let's try 3.
All positive with a remainder of 0.
All positive. All right, so show me. But with zeros at the end?
Yeah.
So what do you got? Read the numbers.
You bring down 2.
Yep.
You multiply it and then you subtract 1, which is positive 1, sorry.
Okay.
Then you multiply 3 to 5 minus 11 is 4.
Good.
You multiply 3 to 4 minus 8 is 4. And then 3 times 4 minus 12 is 0.
Good. So what Kelly recognized here is this, 2 things. You want to name both those things?
There's no remainder.
There's no remainder, good.
It's bound.
And it's an upper bound. So it's definitely a root because there's no remainder. So 3 is one of our x-intercepts. And this tells us there's no x-intercept that's going to be above this. Remember, 0 can be considered positive or negative. Remember that whole idea? So consider it positive. So these are all the same sign. And as a result, this is an upper bound and it's a root. So 3 is one of our roots. So let's box this in at least so we know it's one of our roots. And it's an upper limit. So don't go any further. So when you're looking at the other possibilities like 6 and 4 and 12, you don't have to anymore. So let's go down further now. Let's see. We know that we could, what was our Descartes rule of sign? Told us at most we could have one positive real root. Is that correct?
Yeah.
Right? At most we could have one positive real root. So should I try any other positive numbers? Clearly not. So let's either go to negative 1/2, or negative 1, or negative 2, or negative 3, or one of those values. All right? So what do you want to try? Right, pick one. Negative 2? All right, we bring down the 2. We get negative 4 and negative 1 is negative 5. 10 and negative 11 is negative 1. 2 and negative 8 is going to give me negative 6. Did this one work? Is it? You tried? Okay, good. So we get 12. We get 0 here because we're going to get 12. So as a result, we're going to get the second one that works. Now, the problem we're going to have at this point is getting the two roots if we continue with this table. So what's something that we can do to make it easier on us? This is definitely another root. I agree. But instead of trying in this continuous table, if we get a root, what should we try it in? Who remembers? Some of you did this right on your test. What should I do?
Did you get the depressed equation?
Yeah, so since -2 worked, kind of forget that we did it. Okay, forget that we did it for a second. Take the depressed equation you would have gotten from 3, write it out. Oops. And take it and test -2, the value that we just did see work, in that one instead. You could do this beforehand also. It doesn't matter what order you do it in. You can keep testing roots in the original and then go to this, or go to this first. So we've got 2, 5, 4, 4, and we're going to test -2. Why am I doing this, Nina? Why am I doing this? To find more factors. If this is cubic now, and I get 0 as a remainder, what is this depressed equation going to become? Quadratic. Good word, quadratic. And we can use the quadratic formula on quadratic. So a lot of you forgot to do this. You tested both roots in the original table like we did, and then you said, I don't know what to do, there's something cubic. Well, test this root in the original one that's depressed. So bring the 2 down. -2 times 2 is -4. Plus 5 is going to give us 1. We're going to get -2 and 4 is going to give us +2. We're going to get -4 and 4 is going to give us 0. So yeah, this is definitely a root, and we knew that. But now we have another depressed equation, 2, 1, 2. And that's a lot easier because we can use the quadratic formula with it. Okay, that's my depressed equation from these 3. Set it equal to 0. So I'm going to start listing my roots so I don't forget. I've got 3 and -2 as roots so far. Didn't ask for x-intercept, so I'm going to go ahead and just use a brace instead. Now, I cannot factor this. How do I know, by the way? How do I know I can't factor this? What did we just do a minute ago? Where did we come up with this example? Yeah, we knew they were irrational and imaginary when we made this example up. So, for our sake, it wouldn't even be worth thinking about factoring. Go right to the quadratic formula.
Yes.
Yeah, go right to the quadratic formula for this one. What do you get? I'm going to write it out to start, but tell me what you get. If you can give me something that's exact, so I want a radical in it, I don't want a decimal approximation. I want a radical in it.
-0.25 plus or minus. Is it 0.9 then we get 1, like I.
No, I'm saying, so I want you to do the quadratic formula. That's what I'm saying. I want a square root in there. We get 1 minus 16, which is -15, right? Look under the radical. You're going to get a -15 under there. So this is going to be radical of -15 over a 4. That's what this portion of the division is, and then the other portion is over here. So negative radical 15 means I take out an I, and I can write this as radical 15 over 4i. That's how I would write the other 2 roots. Those are going to go right up here in my solution set. Okay? Again, this is something I'm actually going over because yesterday, me and another math teacher were talking about the difference between exact values and estimates and how many students confuse the two. If a value such as radical 2 is your answer, that is exact. It is precise. But radical 2 as an estimate is 1.414. That is an estimate. Okay, so when you hear exact, please, I hope you all know, it means leave a radical in the answer if it comes about. It also means something like this. If you get 1 over 3 as your answer, that is exact. 0.3 is an estimate. 0.3 with a bar over it, that's exact. You could write that way, that's fine. You follow what I'm saying? Okay? So that's why I asked that problem at the end there. So if you ever ask for exact, leave the radical in it. Okay, an estimate there with decimals is not exact. It's an estimate. How are we doing on time, guys?
Like 10 minutes.
About 10 minutes? You want to do one of these on your own, and we'll call it a day for this, and we'll do the lesson for tomorrow in 5, 6? Does that work? Okay, let me give you one to work on your own. You can just get caught up on your other work and stuff. And we don't have any problems at work to work on yet, so at least you could take off for the weekend, totally. So let's do one. I want one that works. Let me do it on Wolfram again real quick to make sure it works. So let's vary these up. X cubed minus 4x squared plus 6x minus 4 equals 0. How many sign changes do you see? 3. Here's 1. Here's the second. Here's the third. So 3 positive real roots at max. You don't need to have all 3 this way, but you could have 3. Next, switch the signs of all the odd degrees to get the negative function. So in your mind, if you have to do this, or just write it down real quick, anything that's an odd degree, switch its sign. Any sign changes? So we will have 0 negative real roots. Something to point out. We have 0 negative real roots. 0 negative real roots. The 3 positive real roots could be 1 rational and 2 irrational. Or you could only have 1 possibly rational and then maybe 2 imaginary. But those are the only cases that we have in this scenario. Again, all 3 could be positive and real. They could all be rational. We could have 1 rational and 2 irrational. We could have 1 rational and 2 imaginary. But that's it. Remember, irrational and imaginary come in pairs. So if I have all 3 positive and real, and they're all rational, that's easy. But if only one of them is rational, the other 2 could either be imaginary or irrational. So let's go about finding out what this is.
Question, could you skip the part where you change it to negative, like negative x?
I just did. That's in red.
Can you skip that part by
Oh.
speaking, like, you know, if there's...
Because you got 3 for positive and 3 is the highest degree?
Yeah, it's like to the fifth, you can assume there's 2 changes.
I don't know. Let's figure that out. I'm not actually sure. It's a good question. It might be true. It might just be coincidence, though, here. Because could you have 2 negative at max real roots? I guess you could. Because then you could have 1 positive and 2 negative, right? So technically, I don't think you can skip it, but let's see if there's a correlation. I'm not sure. Okay, and I could actually probably look that up and figure out. All right, so in this case, let's go ahead and look at a list of P's and Q's. Rational root test, right? That we did in section 8.7. What are my factors of P?
1, 2, 4.
1, 2, and 4 only. Do I care about the negative roots this time?
No.
I put plus or minus, but do I really need the minus here?
No.
Why not?
Because there's 0 negative.
Because there can't be any negative real roots. So this is limiting my search domain. So look at this now. This is simple. If there are rational roots for this one, they're either 1, 2, or 4. Isn't that really nice and easy? Okay, let's try 4. Let's try 4. Doesn't matter which one. I'm just picking the highest one. Okay, let's try 4. How do I try 4? What kind of I make a synthetic table. I was going to say what kind of a table do I make. So I put my coefficients across the top. My coefficients were 1 of the original, not the one that we changed the signs for. 1, negative 4, 6, negative 4. And let's plug a 4 in. See if 4 is one of the roots. Bring down the 1. 4 times 1 is 4, plus negative 4 is 0. 4 times 0 is 0, plus 6 is 6. 4 times 6 is 24. 24 plus negative 4 gives me 20, doesn't it? Does that work? It doesn't. So that's not it. So let's go to the next one. So you know what? I'm going to call this now something else. I title this, I give it a new name. I like to think of it as a synthetic running table. Continue. Just draw an arrow down. Now try the value of, let's try 1. Okay? Let's try 1. So at 1, we bring down the 1. Again, still bring down this 1 from the top, always. Remember, this always comes down. 1 times 1 is 1, plus negative 4 gives me.
Wait, where is that? Is the one coming from just another possible root?
Yeah, we're pretty much, this is one of the 3, remember we had 3 possible roots right here?
Alright, yeah.
Remember these 3 were possible roots? So 1, 2, or 4. I just chose 1 next. I'll choose 2 after that.
2 works.
2, okay, thanks for spoiling it for us. 1 times 1 is 1. I'm doing this for a reason. Give me a second. 1 times 1 is 1 plus negative 4 gives me negative 3. 1 times negative 3 is negative 3 plus 6 is going to give me 3. 1 times 3 is going to give me 3 plus negative 4 is going to give me negative 1. Now, the reason that 2 is going to work and the idea behind it is as follows. Look at the sign of the remainder. What happened? It went from, what is the remainder really a representative of? That's what I went over for the test.
Yeah, x or the y coordinate.
Y coordinate. If the y coordinate changes signs, what does that mean? If the y coordinate changes signs, so here's your x-axis. Where is a positive y?
Oh, it's past the
Where is a positive y? Up here. Where's a negative y? How do you connect them? By crossing the x-axis. This is called the intermediate value theorem. Something you're going to learn in pre-calculus and calculus. So, Kelly, you picked up on that 2 work, right? Well, look, didn't a sign change? So that means that somewhere between 4 and 1, there's going to be a root. What does that root happen to be? 2. Whenever there's, write this down, please. When the remainder shows a sign change, that means there's a root between those x values that you tested. When the remainder shows a sign change, there is a root between the x values you tested. Now, let me also specify. It doesn't have to be 2. If 2 didn't work, then it means the root that's between there is irrational. Remember, these are only the rational roots we're testing. 1, 2, and 4 are the rational roots that we're testing. So if 2 did not work for some reason, that means that what is between 4 and 1 is an irrational root. Go ahead and put 2 through the table. Second thing to write down, so you're running 2 through the table, sorry. When you do that, you're going to have 1, 2 times 1 is 2, minus 4 is negative 2. Negative 4 and 6 is going to give me 2. 4 and negative 4 is 0. Okay, so we write down that this is a root clearly. Now, other things to jot down. 2 more rules. These are called boundness rules. So we have a lot of rules so far, you notice? The first rule of the change of signs gives us the most positive possible values. The next rule, if we flip the odd degree, and we see the change of signs gives us the most negative possible real roots. If we see a change of sign in the remainder, we know that there's a root between, and that was the third rule. The fourth and fifth rules. Look at the signs of the synthetic row. What do you notice the signs of this row? They're all what? Let 0 be positive or negative. All the signs of this row are, the signs on this row do what? Alternate. When all the signs are positive, write this down. When all the signs of your synthetic row are positive,
It's imaginary.
not imaginary. When all the signs are positive, it means that the number you tested is called an upper limit. When all the numbers in the row are positive, 0 can be positive or negative, okay? Doesn't matter. So if 0 is in this row, it can be positive or negative also. So you can consider 0 either one for alternating. If all the signs are positive, the x value you tested is called an upper bound, which means that the only roots that can exist are below that number. Don't test anything above 4, it means. So if your P over Q values, instead of just being 1, 2, and 4, what if they were like 1, 2, 4, 8, 16, hypothetically? When you test 4, you get all positives, or all negatives, but all the same sign in a row. It means don't test the number above 4. Nothing above 4 will work. Again, if the synthetic row has all the same signs, the number you tested is an upper bound. So test the number less than that next.
How do you know if it's a lower bound?
If the signs are alternating.
Alright.
That was the next rule I was going to go over. Okay? If the signs, the second rule, write this down. If the signs in a synthetic row are alternating, the number you tested is a lower bound. Therefore, test other numbers greater than that value. So when we plugged in a 1, we got alternating signs. So that meant that test above 1. And what did we test? We tested 2, and it worked. Questions? 5 rules from Descartes' rule of signs. The 2 for the alternating signs in the polynomial, the intermediate value theorem, which is if you have an alternating sign for the remainder, that a root must lie between these numbers. And then the last 2 rules, if all these are the same, it's an upper bound. If these are alternating, it's a lower bound. Remember, 0 could be considered positive or negative. Just make it work for you. So if this was 0 or this was 1, 0, 3, negative 1, that would be alternating still. We could consider 0 to be negative in that spot. Okay? So again, if this were 0 right here, you can consider that 0 as a negative, make it positive, negative, positive, negative. So 0 works in your favor, whichever way it needs to work. What are the other 2 roots? Well, 2 is one of the roots. Let's take a look at our depressed equation from this. Let's finish this off. The depressed equation is x squared minus 2x plus 2 equals 0. Remember from here. There's a depressed equation always. If this had not been x to the 3rd to start, if it had been x to the 4th, I can't do this. I need to take the bottom row, the one that worked, and make another table out of it and test again to get a further depressed equation. Remember, every time you test, you get 1 degree less. If you start x to the 4th, the depressed equation will be x to the 3rd. A lot of you did that in your test. You can't do anything with x to the 3rd. You got to do it again. Run through a table with x to the 3rd equation to get x squared next. And then you can get the last 2 roots. Here it's x squared, so let's just get the last 2 roots. Can this factor? Can this factor? Hello, can this factor? Why not? Why do you know it can't factor? What were the only possible rational roots? 1, 2, and 4. Didn't we test them all? When something can factor, it means the roots are rational. So since we tested 1, 2, and 4, and 1 and 4 didn't work, and 2 did, we've expunged all of our possible rational roots. So by default, this can't be factored. It's got to be using the quadratic formula. You see what I'm saying there? When you can factor, it means the roots are rational. Since we only have our 1 rational root already, the other 2 didn't work, you can't factor it. So don't even really try. So go right to this. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Simplify this, please. Oh, c should be positive. I apologize. Hold on. Make that positive. 4ac should be positive there. So we've got 2 plus or minus 4 minus 8 under a radical. So what kind of an answer am I going to get? Imaginary. Okay, 2 plus or minus root negative 4 over 2. Continue simplifying. What's the square root of a negative number? I write it as what? I. With the positive number underneath. Well, the radical 4 is just simply 2. There's my other 2 roots. Okay, just keep simplifying, please. 2's all cancel out here. Factor out a 2 out of the top. The 2 cancels, or just recognize that every term has a 2 in it, so they all cancel, leaving 1 plus or minus I. Does this make sense? This was a long example for one. I want you to do one of these examples tonight. Okay, just one of them. That's all your homework is. Now, what I want you to do is the 5 things that we did. I want you to first start by testing for the positive and negative real roots. Then, use the rational root theorem to come up with a bunch of rational roots. Try some of them. Don't use your calculator. If you get all positives or all negatives, you know that's an upper limit, so try another rational root that's below it. If you get alternating signs, it's a lower limit, so try rational roots above it. If you get a sign change in the remainder, pick one of the rational roots that's between there to try. Does that make sense? Yes, no, maybe so? Okay? The one I want you to try is the following. Let me make sure this works before I give it to you. I want you to try x to the third minus 5x squared plus 3x plus 2. Let me see if this works first, but write that down. X to the third minus 5x squared plus 3x plus 2. Perfect. It will work. Okay? It will be an interesting equation you're going to get here. Okay, so please try this one tonight. That's all your homework is. But repeat literally what we just did with that example. Okay, tomorrow we'll start with section 5, 6, I think it is.